Today's talk is about Snudda, which is an open source tool for creating microcircuits in silico. And my name is Johannes Hjort, and I'm at the Royal Institute of Technology in Stockholm. And this talk has been pre-recorded, and you can find it also on YouTube. So there's a QR code here, which links to a web page on GitHub, which in turn links to the video, and additional resources if you want to find out more about Snudda. And let me start by some acknowledgements. So I work in the group of Jeanette, Helger, and Kotaleski. Both Alexander and I work in close collaboration with Jeanette, Sten, and the PhD students at both KTH and KI. And we are funded by the HPP and the Swedish Research Council, among others. Snudda is a tool to create large networks of neurons, and we use the morphologies to guide us where the synapses should be located between these neurons. And to do that, we do voxel-based touch detection, and then we do rule-based pruning of synapses to reduce the number of putative synapses to the ones that are realized in the network. We also have some script for network analysis, and then finally you can run the network using the neuron simulator. So all of this is open source and it's available on GitHub, and you can run it on Linux, Mac, Windows, but also on supercomputers. So in order to create these networks of neurons, we will need detailed morphologies. So we would need dendrites and preferably also axons that we can do touch detection on. In addition to that, because we want to simulate this, we will need electrophysiological neuron models. In our case, these are optimized using BluePyOpt. We also need synapse models because we're going to connect the neurons together. And it's very good to have connection statistics so we know sort of how much we should prune the network. So the voxel-based touch detection works by dividing the space into voxels, and then it draws these neurons in this voxel space and looks for overlaps. So on the left-hand side here, you can see two very simple neurons, ball and stick figures, for illustration purposes. So you can see the axon and you can see the dendrite and the soma, and you can see that when they overlap, we want to find the synapse. And internal in Snudda, it looks more like this. Here you can see the voxel representation of these, and you can see that it found synapse where they were overlapping. So the space is divided into these voxels, which are 3 by 3 by 3 micrometers in size. And of course, the neurons we use in the network creation are much more detailed. So here on the right-hand side, you can see a dSPN and an iSPN touch detection between them, and you can see the synapses placed there. So we place all these neurons within meshes to get the realistic shapes of these structures. And these meshes are from Allen Brain Institute. So here you can see the stratum, and in order to speed up our generations of networks, we divide the space into hypervoxels, which is 100 by 100 by 100 voxels. And here you can see that hypervoxel, and you can see roughly the amount of somas that are located within such a hypervoxel. And if you add the axon and dendrite, you can see that it's quite a complex structure. So if you look within the entire mouse stratum, you have about 1.7 million neurons. And if we do a touch detection, we get 31 billion putative synapse locations. But of course, all these synapse locations are not real synapses, so we need to prune them down to match the connected statistics in experiments. And to do the pruning, we have set of pruning rules, which I will talk about here. The probability of keeping a synapse is a product of all these factors. So to illustrate this, we have again these simplified ball and stick neurons organized in a very regular fashion. So you can see that they both have 2 axons and dendrite branches, which means that each of these pairs are connected by 4 synapses. So the first rule I'm going to illustrate here is the F1 rule, and that just removes randomly a fraction of the synapses. So if you have F1 0.5, it means you keep half of the synapses. So you go from 400 to 200 synapses. If you have F1 equals to a quarter, you will keep a quarter of the synapses. So in this case, it's randomized to be 96 synapses. So now it gets a bit more interesting, because now we're going to combine it with the P-mu2 rule. And the purpose of this rule is that it will make sure that there's not too few synapses between a coupled pair. So if you have P-mu2 equals to 3, it means that if you have 3 synapses between a coupled pair, it's a 50-50 chance that you will keep those synapses. And if the fewer, you're more likely to remove all synapses, and if there are more connecting this pair together, you're more likely to keep all the synapses. So you can see if you apply this rule when f1 is equal to 1, some of these ones that are connected by 4 will be removed, but most of them will be kept. If you instead have a scenario where you already removed half of the synapses, when you then apply a mu2 equals to 3 rule, you get a considerable sparsening of the connectivity. And even more so if you have f1 equals to 0.125. And you still have here have mu2 equals to 3, so you get a considerable reduction in the number of synapses. And then we have the softmax rule, and this is just to sort of limit the upper number of synapses. So as you reduce softmax, you can see that it reduces the maximum number of synapses in a random fashion. So those two, the PMU and SM rule, they can shape the distribution of the number of synapses between a coupled pair of neurons. The next rule, the A3 rule, you can use after you've done the first step. And this lets you shape the connectivity, so the probability of connections between a pair of neurons in the structure, because you might not want to affect the number of synapses that are between a coupled pair. So what it does, it tells how many of the coupled pairs we're going to retain. In the case of A3 equals to 1, we would keep all the coupled pairs. If A3 is equal to half, it means that half of the coupled pairs are kept, and the other half, we have all the synapses removed. And for A3 equals to 0.25, we keep 25% of the coupled pairs, and all the other ones have all their synapses removed. So this wouldn't affect the statistics of how many synapses a coupled pair have. It only affects how many coupled pairs there are in the structure. And then finally, some neuron pairs might have preference to proximal, medial, or distal synapses. For instance, FS prefer to connect proximally on SPNs. So then you could use something like this to sort of shape your distribution of synapses. So these are the different tools we have to sort of shape the connectivity. And we want to match it to experimental data. And one set of experiments that are very useful is when experimentalists have done pairwise recordings. So they patch two neurons, inject one of them with a current injection and see if there's a response in the neighboring neuron to determine whether they are coupled or not. And by doing that on many neuron pairs, we can get some information about the connection probability. So here you can see experimental data, the red lines. So it's been binned. So they just reported within 50 micrometers, they have a certain connection probability, dSPN to dSPN. And another study looked at within 100 micrometers. So we tried to sort of match this data with the pruning rules. We also might have some information about the number of synapses there should be between coupled pairs, and also how many coupled neighbors there should be of a certain neuron type. So all of this we try to sort of replicate the experimental data. And finally, we also do virtual experiments where we might do a current injection in one neuron and see what is the response in the neighboring neurons to see that we actually have the correct coupling strength between different neuron pairs. And then, of course, you can run the simulation. So here is an example of a 10,000 neuron simulation. And we have cortical and thalamic input, and we also have a bit of neuromodulation. So in this case, dopamine will increase the dSPN activation while it will reduce the iSPN activation. You can see here some traces from the different neuron types. So next I will tell you a little bit about how to actually set up your own networks. So there's two ways you can do it. You can either do it through the command line, and this shows you the commands you will need to do to generate such a structure. So the first step is to create a config file, which you do with Snudda init, and here you specify the size. So in this example we picked 10,062 neurons to match the density, and then you place them. After that you want to do the touch detection, and this step can take quite a bit of time, especially if you run it in serial, so you probably want to parallelize it. And this is the pruning step, which then reduces the number of putative synapses to match experimental data. And then finally, if you want to run a simulation, you want to generate the input and then simulate. So to generate the input, you also need an input config. So here I show you how to step by step do it in a serial mode, but of course you probably want to run it in parallel. And to do that, you need to add a few more extra steps. First of all, you need to start IP cluster, and you need to set up a few environment variables. So in this case, I run it on my local machine. So we start the IP cluster first, and then when we run place, detect, and prune, we add a parallel option here to tell Snudda that it should run in parallel. And then it will use these workers. And also for the input generation. And here you can see that we copied over an input config file to the simulation directory. And then finally we stop the IP cluster, and then finally we start the neuron simulation here. So that was the first way, that was to use the command line, but you can also run it through Jupyter notebooks. So I will show you here some examples. So if you go to the web page, so if you go to the Snudda GitHub repository, Snudda examples notebooks, and scroll down here, we have a list of different notebooks with examples of what you could be running. So I will talk you through the simple network creation and also the parallel network creation and how to run the simulation and how to visualize a little bit of it. So here's an example of a simple network creation using a Jupyter notebook. So in this example, we're going to create 100 dSPNs and 100 iSPN neurons. We are not going to add the FS, LTS, and ChIN in this particular example. The first step we do is we write the config file, and the way to do that is by using Snudda init. We want to define the stratum with 100 dSPN, 100 iSPN. We also specify a random seed so that we can replicate the network if we want to run it again. And because we run such a small network, we don't use the real mesh, we decided to use a cube instead. So this cube will be resized automatically to have the correct density. And after that, we run Snudda place, which then places the neurons within the volume and writes a network position file. And then we can run Snudda detect. And as I mentioned before, when you run Snudda detect, it divides the space into hypervoxels, which contains a million voxels. And it does touch detection on those one by one. In this case, it's just a serial way of doing it. And then finally, we do the pruning, and you can see that here we only keep about 5% of all the synapses detected. And this is a visualization of what it looks like. So of course, you don't want to run large networks in serial, you want to run it in parallel. And this notebook shows you how to set up the network in parallel. So first of all, in the terminal window, you need to start IP cluster. And then after you finish, you need to stop IP cluster as well. And within the notebook, then you set some environmental variables just to tell Snudda about this configuration. So again, we initialize a network. And in this case, we do 200 neurons instead, just to do it slightly bigger, and we added 4 FS neurons also. So this will just write the config file for this. And then we connect to the workers here. So we create this RC client. This is then passed to place, detect, and prune so that they are aware they are running in parallel. So the difference, if the only real difference compared to the simple serial version, is that now we pass an RC variable here, and this will then be used to run it in parallel. And the printout, we're suppressing hypervoxels, which take less than 100 seconds, otherwise there would be a lot of printouts. So you do the Snudda detect, and then you do the Snudda prune, and again, we kept about 5% of the synapses, whereas we kept 43% of the gap chunks. So the gap chunks are between FS neurons. And here you can see a plot of the network. Then we want to generate some input to run a simulation. And here there's an input config file which is already predefined. You can have a look at it by yourself if you want to. And this just sort of sets up the input. You need to compile the mod files. And then you can run the simulation using MPI exec. So this will run it in parallel. And this is a very crude plot which shows you that we finished the simulation, we had some network activity. We can also visualize, let's see if we have a Blender visualization here, Blender example. So you can also visualize the network using Blender. And here we have a small network where we have chosen to visualize neuron number 0 and 7. And then you get something like this. And you can also show where the synapse is located. But if you want and feel like you have a bit of time, you can render the entire network. And depending on how large the network is, this may or may not take a lot of time. And then you can get something beautiful like this. So there are a lot more Jupyter notebooks available with examples for how to do different things like density variations, rotations of neurons based on where they're located in space, etc. So please have a look, and if you have some questions, I will be available in the chat. Thank you very much for listening.